Hello everyone, what's up? Good to see you all once again. Today we'll be continuing with our chapter inverse trigonometric functions and we'll be dealing with some of the identities involving inverse trigonometric functions. You must have studied the identities involving simple trigonometric functions, and the same is the case with the identities of inverse trigonometric functions. Okay, so I'll be writing down all of the identities and which will be included in this chapter. The proofs of these identities are less likely to be there in your exam, but if you still find any identity hard to prove, so you can DM me and the link is given in the description. You can DM me on Insta. Okay, so firstly we'll start with very simple thing, that is sine of sine inverse x is always equal to x, and same is the case with all other inverse trigonometric functions. Simply, as we know that 1 upon sine x is cosecant x, same is the case with sine inverse x, but here the angle is reciprocated, not the trigonometric function itself. So sine inverse 1 upon x is cosecant inverse x. Similarly, cos inverse 1 upon x will be secant square x, and tan inverse 1 upon x will be cot inverse x. Okay, so these were the basic identities that were involving inverse trigonometric functions. After that, we have got other identities as same in the simple trigonometric functions, like sine inverse minus x is equals to minus of sine inverse x. Cos inverse minus x is equals to pi minus cos inverse x. Yeah, it's a bit changed, so just keep this thing in mind. Then after we get tan inverse minus of x is equals to minus tan inverse x. Then we got secant inverse minus x is equals to pi minus secant inverse x. Yeah, it's a bit different again. Then we have got cosecant inverse x, which is equal to minus of cosecant inverse x. Then it's cot inverse minus x, which is equal to pi minus cot inverse x. Okay, these are the identities. So you can learn that if there is a negative sign in the angle of an inverse trigonometric function, how you have to deal with it, right? Let's move ahead. Now next are the identities involving addition. So sine inverse x plus cos inverse x is always equal to pi by 2. So just keep these identities in your mind for time being as well, because we'll be doing some of the examples, and that's why you need to remember these identities before attempting the sums. Next one is tan inverse x plus cot inverse x is equals to 90 degree again, and then it's cosecant inverse x plus secant inverse x, it's again equal to pi by 2. So these are the identities involving addition of trigonometric functions, and similar to these there are others like tan inverse x plus tan inverse y is equals to tan inverse x plus y upon 1 minus xy, and same is the case with identity involving subtraction of tan inverse y is equals to tan inverse x minus y upon 1 plus xy. Then if it is 2 tan inverse x, now here are three identities of 2 tan inverse x, so I'll write them collectively. First is tan inverse 2x upon 1 minus x square. Then next is sine inverse 2x upon 1 plus x square, and the last one is cos inverse 1 minus x square upon 1 plus x square. So here you can see that 2 tan inverse x is a very multifaceted and a very versatile identity, so because it involves sine, cos and tan itself as well, right? So this is it, we are done with the identities, and now we'll be implementing these identities on the sums. I have written all of these identities so that you all can write down and you can make a list so as to remember these identities easily. All right, so let's move to our first example, that is example third. Here is our first sum of third example. In this, we have to show that sine inverse 2x under root 1 minus x square is equals to 2 sine inverse x. So in this, you have to substitute x with a trigonometric function, and you have to take it as sine theta in this sum. Now, how will you remember that we have to substitute x with sine or cos or these kind of trigonometric functions? Here is the thing: when you get this term 1 minus x square in the statement, you have to understand it automatically that there will be sine or cos substituted, because you know that 1 minus sine square theta is equals to cos square theta, and 1 minus cos square theta is equals to sine square theta. So that's why when you will get a trigonometric function which is having square on its top, then you can cancel under root very easily. So that's why this is a kind of hint or trick, you can say that, so that you can just give a gesture to yourself that you have to substitute it as sine theta or cos theta. Now we have to substitute x is equals to sine theta. What will you get? Sine inverse 2 sine theta under root 1 minus sine square theta. So 1 minus sine square theta is cos square theta, and root will be cancelled. You will get cos theta only. Sine inverse 2 sine theta cos theta. Now I am pretty much sure that you are aware of this identity, that is 2 sine theta cos theta is equals to sine 2 theta. You will get sine inverse sine 2 theta, and what was theta? That will be sine inverse x, right? So sine and sine will be cancelled, because we have learned the identity just now that sine inverse sine x is equals to x only. So here x is 2 theta, and what will be theta? That will be sine inverse x. So yeah, that's our right hand side, correct? This is how we can prove these kind of sums. And what's the statement of second sum? In the statement of second sum, the left hand side is surprisingly same, but we have to prove it equal to 2 cos inverse x. So now you can take a hint that you have solved it using sine theta. Now you have to solve it using cos theta. So substitute x is equals to cos theta. On your NCERT, they have just left this sum for you guys, but I'm solving it for you. So yeah, x is equals to cos theta. What will you get? Sine inverse 2 cos theta under root 1 minus cos square theta, then sine inverse 2 cos theta. So 1 minus cos square theta, that is sine square theta, and root and square will be cancelled. You will get sine theta only, because it's 1 minus, actually we have substituted x is equals to cos theta, right? So we'll get sine theta only, and sine inverse of sine 2 theta, because 2 cos theta sine theta is equals to sine 2 theta, which will again be equal to only 2 theta, and here theta is cos inverse x. You will get 2 cos inverse x, which is again equal to your right hand side. So yeah, you can see that how easy are these sums. You only have to know that how to apply some of the identities, and of course you have to keep those identities in your mind before implementing them to the sums, right? So let's move ahead. This is our following example. And in this example, we have to prove that tan inverse 1 by 2 plus tan inverse 2 by 11 is equals to tan inverse 3 by 4. Now this statement, the left hand side is very simple, and you can compare it easily with tan inverse x plus tan inverse y. What was the identity? Yes, tan inverse x plus y upon 1 minus xy. So here x is 1 by 2 and y is 2 upon 11. So can we just simply substitute the left hand side with the identity by using the property, right? So tan inverse x plus tan inverse y, that is equal to tan inverse x plus y upon 1 minus x and y, correct? So just solve it a bit. Actually the whole thing is inside bracket, okay? So don't get confused, because tan inverse is the only trigonometric function and this whole is the angle. So tan inverse, now take the LCM, as you can see that it's 22, and then you can write 11 minus 4, 11 plus 4, and upon 1 minus 2 upon 22. You can see 22 minus 2. So we'll form a step more, that is tan inverse 11 plus 4, that is 15 upon 22, then upon 22 minus 2, that is 20 upon 22. You can clearly see that 22 and 22 will be cancelled, right? So you will be only left with tan inverse 15 upon 20. Now when you will do the cutting or the divisibility, you will get 15 and 20, that will be 3 upon 4, because 5 3s are 15 and 5 4s are 20, so which will be equal to tan inverse 3 upon 4. So this was the right hand side which we were desiring to prove, so which is equal to right hand side. So we did nothing, we did literally nothing, because a student who does not know the identity of tan inverse x plus tan inverse y, he or she will not be able to do this sum utterly. But here we did know this identity, so that's why we just conveniently applied that and we got our result. This is our next example. We have to express tan inverse cos x upon 1 minus sin x in the simplest form. Simplest form means you have to simplify as much as you can. Okay, so it should not be containing these kind of terms in fractions or some typical or complicated terms like these. So it must be simplest form. Now we'll simply solve it using a formula and applying various identities to this. Firstly, we'll change cos x and the whole fraction which is inside the angle. So tan inverse will be the same. And now you know the identity of cos 2x. Now cos 2x is equals to cos square x minus sin square x. Correct? It means if here is angle 2x and then here the angle will be half. It means if it's 2 then it will be 1. Now if there is angle 1, so the angle will be x upon 2 here and x upon 2 here as well. So we can write cos x is equals to cos square x by 2 minus sin square x by 2. Yep. Yeah, easily, because the angle is half. Here angle was 1 and we have just halved it and we got x by 2 and x by 2 here only. Now we have formed a term involving cos square and sin square. So can we also change 1 as cos square x by 2 plus sin square x by 2, because cos square theta plus sin square theta should be same. It's always equal to 1. Okay, and what was the identity of sin 2 theta? Yeah, we have just seen that sin 2 theta is equals to 2 sin theta cos theta. Again, yeah, I'll write it for your convenience that sin 2 theta is equals to 2 sin theta cos theta. If here it's 2 theta, then we'll just take its half and then the theta will become only 1 theta and 1 theta. Now here it's only sin x. So here it will become x by 2 and x by 2, correct? So it will be 2 sin x by 2 cos x by 2. Yeah, so this is how we have started the simplification of our given term. And now you will see that what you get. Tan inverse. Now it's a square minus b square, right? So a plus b and a minus b, correct? And in the denominator, yeah, you must be already seeing that a square plus b square minus 2ab, you will get a minus b whole square, correct? Now these terms will be cancelled. You will only get cos x by 2 plus sin x by 2 divided by cos x by 2 minus sin x by 2. Now while attempting the sums involving trigonometry or inverse trigonometric functions, just keep one thing in mind, that whenever you come across any term like this, just divide the numerator and denominator with cos theta. Whatever the theta is being used, just divide it with cos theta. So when you will divide this by cos theta, you will get only 1. Then plus sin x by 2 upon cos x by 2, you will get tan x by 2. And what will you get here? That is 1 minus tan x by 2. Similar as numerator. Now 1 plus tan theta over 1 minus tan theta, that is very well known identity of tan pi by 4 plus theta, that is x plus 2. And then tan inverse tan x is always equal to pi by 4 plus x by 2, which is the required simplest form, because I don't see anything more simpler than this. Okay, so yeah, the game is all about identities, nothing else. We have yeah, you have seen that we have formulated many identities from our own by just dividing the thetas by 2, and just by taking the halves of the theta. Yeah, so this is what you have to do. We have literally applied each identity in every single step of this sum. So if you are unaware of the identity, so kindly just make your that part strong. Now, I have told you in the previous example that whenever you will see some statement like 1 minus x square, just substitute it with sine theta or cos theta. So in this case, now you can see the statement involving x square minus 1. So in these kind of cases, mostly go for secant theta, because you know that secant square theta minus 1 is equals to tan square theta, and that will really help us in cancelling the square root, right? So simply put x is equals to secant theta. Nothing can be more simpler, I guess. Then what will you get? Cot inverse 1 upon root secant square theta minus 1, which will be equal to cot inverse secant square theta minus 1, that is tan square theta, and tan square theta will become only tan theta. So 1 upon tan theta. You know very well that 1 upon tan theta is equals to cot theta. Again, cot inverse cot x is only equal to x, that is only theta. What is theta? Here it is secant inverse x, which is the simplest form. So you have seen that how simple this sum was. Yeah, you must be wondering about that tune. That was a call that I got in between, so sorry for that. And yeah, this is the simplest form that we have got, because here it's no fraction in the angle and nothing. Yeah, it is the simplest form. So it's very easy to reduce any given inverse trigonometric function to the simplest form, because you only have to know about the identities and identities, nothing else. It's example 7th, and we have to prove that tan inverse x plus tan inverse 2x upon 1 minus x square is equals to tan inverse 3x minus x cube over 1 minus 3x square. To prove this, we'll use the basic technique in which we first consider left hand side, right? So what is left hand side? That is tan inverse x plus tan inverse 2x upon 1 minus x square. Now we have recently done the identity tan inverse 2x upon 1 minus x square, that is 2 tan inverse x. Simply write it, tan inverse x plus 2 tan inverse x. What you will get, of course, 3 tan inverse x. So it cannot be solved further. So now it's automatically understood that we have to consider right hand side, and it's time for the right hand side to step into the picture. This is it, and you can see that this is looking like an identity, because we have an identity that 3 tan theta minus tan cube theta upon 1 minus 3 tan square theta is equals to tan 3 theta. So it's automatically understood that substitute x as tan theta. What will you get? Tan inverse 3 tan theta minus tan cube theta upon 1 minus 3 tan square theta, right? Here, for your convenience, I'll write that we have substituted x is equals to tan theta. Okay. So it will originally become tan 3 theta, correct? So you will get tan inverse and multiply tan 3 theta. Tan inverse tan x is again equal to x only, and what is theta? That is tan inverse x. So yeah, you have got left hand side is equals to right hand side simply. So yeah, 3 tan inverse x. In this way you can prove these kind of sums. So yeah, you must have understood till now that you don't have to know only the identities of inverse trigonometric functions, but also the identities of simple trigonometric functions. So we are left with only one example, and that's very, very easy. Let's finish that, and let's finish this chapter with that. In the last example, we have to find the value of cos secant inverse x plus cosecant inverse x. So secant inverse x plus cosecant inverse x is simply pi by 2. So yeah, it's the simplest sum that you have come across in this video. So cos pi by 2 is simply 0. So yes, we have got our answer as 0. Yeah, so this was the sum only. It took only a fraction of seconds, I guess. So that's why I was saying that it's very, very easy. So now you have understood all the identities of the inverse trigonometric functions and also their implementation. Now I am pretty much sure that you are very much able to attempt all the sums. Still, if you find any problem in any sum, don't hesitate in contacting me through comment section, or you can DM me. The link is given in the description. And don't forget to press the subscribe button before leaving my channel, guys, because it will really motivate me and it will really push me to just deliver these kind of videos on a regular basis for you guys. And also share my channel as much as you can with your classmates, with your friends and other needy students. All right, thanks for watching, keep practicing, and all the very, very best.